Alright, so we'll get started. So the reporter thing, we have 5 minutes to get prepared. Please let us know if you're ready. Please let us know if you're ready. Okay, please start the clock. Stop.
Hello, I'm Woo-hyun from Team Mighty, and it is a great pleasure to present in front of you. The problem I'll discuss today is problem number 1, Gaussian canon. The problem is as follows. The goal of the problem is to optimize the magnetic position for this greatest effect in Gaussian canon. And here, I interpreted the greatest effect to be the largest kinetic energy gain. And this is the flowchart of my research. First, based on observations, I analyzed the phenomenon into 3 phases. And for each phase, I applied conservation laws and considered energy loss and energy dispersion. And from this, I could predict the ejection velocity of the Gaussian cannon. Moving on to experiments, I found a relationship between the magnetic position and the ejection speed, and compared with my theory. And in conclusion, I could optimize the magnetic position for this largest effect as the problem states. And I'll move on to my theory. This is a basic observation of the phenomenon. Here is the magnet, and this is the phenomenon. So, based on observations, I analyzed the phenomenon into 3 phases. The first phase is attraction phase. When a ball is rolled towards the magnet, it is attracted by the magnetic force. And then the second phase is collision. And lastly, the last ball is ejected with specific velocity. First, I analyzed the first phase, the attraction phase. Suppose that the first ball had initial velocity v0, and right before the collision, the first ball gained velocity and became v1, and the magnet had also velocity v2. Then, we could apply simple conservation laws to find out the values of v1 and v2. And as you can see here, first, the rotational kinetic energy of the first ball does not change before and after the collision, before and after the attraction, because the friction force is very small. And also, you can see that there is magnetic potential energy from the left. So decrease in magnetic potential energy results in kinetic energy. during the ejection phase, suppose that the last ball the velocities was v1 prime and v2 prime. And after the ejection, the last ball speed was ve. And to find out the values of this velocity, we could apply the similar conservation laws. And however, in this case, increase in magnetic potential energy results in decrease in kinetic energy. However, when it gets to the second phase, which is collision, the problem is much more difficult. Because in this case, what we have to consider is the energy dispersion and energy loss during the collision. And this is a video which illustrates the phenomenon. As you can see here, not only the last ball, but other balls also gain kinetic energy during the collision, which implies that the kinetic energy of the first ball is not only transferred to the last ball, but also transferred to the other balls. And this means that the kinetic energy of the first ball dispersed through the collision. And also, since the collision between steel balls are not perfectly elastic, so energy is lost through sound and heat during the formation. And to consider these factors, I did simulation on ball collision. First, I suppose that two balls are compressed with distance x. And in previous researches, it is known that the force between these two balls are given by the following equation. Here, the first term is elastic force. It is a conservative force which acts on between the balls. And the second term is dissipative force, which is a non-conservative force, and this causes the loss in energy. And coefficients of each forces are given by constants, and it is determined by the property of the material. And with this equation of force, I could determine the acceleration. I could simulate the ball collision. So I use Java programming here, and this is the simulation result. The y-axis is velocity and x-axis is time. So these 5 lines represent the velocity change of 5 balls during the collision. And as you can see here, not only the last ball, but also other balls also gained velocity after the collision, which means that there was energy dispersion. And also, when you compare the kinetic energy before and after the collision, it has been decreased, so there is energy loss. To summarize my theory, first, in the attraction phase, I use conservation laws to determine the values of V1 and V2 right before the collision. And from using these values as initial conditions, I did simulation on ball collision and find out the value of V1 prime and V2 prime. And finally, during the third phase, I again used the conservation laws to finally determine the ejection velocity of the last ball. And now I'll move on to experiments. First, in my theory, it is very essential to determine the value of magnetic potential energy. So what I did is to measure the magnetic force versus distance. And so I put thin films between the ball and magnets to give initial separation and measure the force with Pascal force sensor. And the graph is shown as follows. As you can see, as the distance gets further, the magnetic force partially decreases. And when we represent this with log scale, then we can obtain the following linear graph, which means that the graph can be shown as a form of power series. So the power series fitting, and from integration, I could approximate the magnetic potential energy of the ball and magnet. And for the second case, I put another ball between a ball and magnet and did the same thing. And I used straight Dolio method to approximate the magnetic potential energy. And moving on to the real experiments. So to measure the velocity of the ball before and after the collision, I used Pascal photo gate, and I also used the plastic rail with initial inclination to give constant velocity. These are the two photo gates I used, And here, the first photo gate is used to determine the initial velocity before attraction, and the second photo gate is for ejection velocity. And the variable controls, I control the variables like steel ball and initial velocity, and I changed the number of balls in front of and behind the magnet, and found the relationship with ejection speed. And again, the number of balls in front of the magnet and the number of balls behind the magnet specifies the magnet's position. And this is the result for experiments changing number of balls in front of magnet. Here in the diagram, this green ball it means the magnet. And as you can see, when there was put a ball was put in front of the magnet, the ejection speed partially decreased, which means that ball in front of the magnet causes less magnetic potential energy, and it causes the slow speed. So to optimize, there should be no ball in front of the magnet. Moving on to the second experiment, I changed the number of balls behind the magnet, and here x-axis is number of balls behind the magnet, and y-axis is the ejection speed. As you can see in the graph, my theory and experiment matches very well, with error ranging from 0 to 5%. And so with my theory, I could accurately predict the ejection speed. And to optimize, I should consider the kinetic energy of the last ball. And this is the kinetic energy of the ejection ball. And as you can see, even though the initial kinetic energy was very small, it gained velocity through the collision or Gaussian cannon. And here, we can see that my theory also predicts the kinetic energy very well with an error 10%. And here, we can see that when there are two balls behind the magnet, its kinetic energy is smaller than before. And this is because of the strong magnet binding, the last ball loses its kinetic energy as magnetic potential energy. However, when it gets too many balls behind the magnet, the kinetic energy also decreases. This is because the energy loss has been occurred from the collision. And to optimize the magnet's position, there should be 3 or 4 balls behind the magnet. And the reason why I put 3 or 4 balls is because the actual velocity change difference is not that big, it's about 0.01 meter per second. So the optimization is like this. And now I'll conclude my research. In conclusion, my theoretical model very precisely predicts the ejection velocity. And also to optimize the magnet's position, as the experiment and theory shows, there should be 3 balls put behind the magnet, and there should be no ball put in front of the magnet. And my theory could also be applied to other researches as well. And these are my researches, references, and thank you for listening.
Okay, the opponent team, please feel free to ask questions to the reporter.
Understand that you assume that the initial rotational energy is the same as the ejecting rotational energy. Did you ever check if there is actually rotational energy, if it is actually the same?
So, in fact, I'll show you later, but when you consider the friction force when the magnet is pulled through the ball, then I calculated the energy loss from the friction, and it is very small. It is about 1/80 of the magnetic potential energy. So that will not cause the rotational energy to decrease. So that's what I meant.
Okay. Do you think that I know that you mentioned magnetic potential energy.
Yeah.
Do you think that magnetic force is a conservative force?
No, it isn't, but the magnetic force?
Yes.
But the magnetic potential energy, what I meant in this research, is what I defined to be. And I defined the magnetic potential energy of the ball when it is attached to the magnet to be the amount of energy to separate the two ball from the magnets.
Okay. Can I see the slide where you measure the force with this thin film? Can I see the picture?
Yeah.
Did you fix the magnet in this case?
No, it isn't.
Then how? I don't understand how you measured the force.
So I fixed the other end of the string to be here. There is force sensor, and I pulled the magnet with hand and measured the maximum force needed just before the separation.
Okay, thank you. The opponent team, please take a couple of moments to prepare. Okay, opponent has the floor. Please begin.
Hello, my name is Hyunjun Park from Team Format, and I will address the problem of the Gaussian cannon. First of all, the reporter had many strong points and weak points in this wonderful report. One of the strong points was that he used a video and diagram, and it was easy to understand the phenomenon. Also, there was some correlation between the theory and the experiment. Also, he had fluent speaking, and he used mathematical equations to support each point. However, there were some questioning points in this case. Because there is friction, rotation energy always exists, and it can affect the magnetic force. I wonder if you ever thought of that. Also, it does not mention how dipole-dipole interactions can change the change as the magnet rotates as the ball approaches the magnet. Also, it did not elaborate the exact effects of the eddy current in the system. One of the points that I would like to discuss is that, did you ever consider fixing the magnet? Would that not have aided in your optimization for the greatest energy, kinetic energy? Also, I also like to question in your slide, why is the experimental velocity higher than your theoretical velocity? I would like to question that. And this is basically a fundamental question. Do you think, as a ball approaches a magnet, do you think the energy will be conserved? And basically, do you think that magnetic force is conservative force? Also, did you directly observe the ball rotating as it approaches this magnet in the experiment? Because the rotational energy can be converted into kinetic energy and change some of your theories. If the ball can be considered as a magnetic dipole, would there not be a change in magnetic force as the ball rotates? I'd like to ask you that. And also, I would like to ask you about the effects of eddy currents in your system. Okay, for the questions about the experimental apparatus, I would like to question the exact material of the railing, and how did you find the magnetic potential from the force? Also, I have some questions about how you measure the force. And with an infinite velocity, this is a fundamental physical question. With an infinite velocity,